Okay, let's get started. So, welcome to multi-perspective reasoning in knowledge representation, an introduction to standpoint logic. I'm going to be teaching the first two lectures, and Hannes Straß will be teaching lectures 3 and 4 on Wednesday and Thursday. There is a website for this course, which I've written the URL up on the blackboard over here to the left. You can download course materials there if you'd like. You can download the slides and also reading that is relevant to the various material we will be discussing. Okay, so I'm having a technical malfunction. One moment. I'll just give you a brief overview of the first and second lectures. So what we're going to talk about today is knowledge representation, which is a particular area of computer science and theoretical computer science. And we will talk about an interesting problem in this area called knowledge integration, which standpoint logic has been introduced to solve. So after going a little bit over KR, just at a high level, explaining what KR is about and what the knowledge integration problem is, I'll introduce to you propositional standpoint logic, which is a fairly rudimentary form of standpoint logic. It's an extension of classical propositional logic with certain modalities. And it will serve as a basis for the rest of the lectures in more expressive standpoint languages that have better modeling capacity and knowledge representation. We'll then talk a little bit about the proof theory, so we might have some time to get to that today, which is a proof system. So this constructs proofs that witness validity of standpoint formulae and allows for one to carry out reasoning in a formal fashion. And even this reasoning can be automated, as we'll discuss. And at the end of these two lectures, I'll talk about first-order standpoint logic, which is an extension of propositional logic with universal and existential quantification, along with relations between entities. So this is a very expressive language which has a lot of modeling capacity. We'll talk a bit about how it can be used to model what are called knowledge bases. Okay, so let's talk a little bit about knowledge representation. What is knowledge representation? I've given a quick definition at the top of the slide. It's the study of how to formally represent information about a domain of interest in a way that enables automated reasoning and inference. Okay? So what we do in knowledge representation is we find some area that we want to encode information about or knowledge about, and we encode this information in some logical language or formal language, which represents the entities within that domain as well as the relationships that they stand within or with respect to each other, and also is accompanied by a logical theory that talks about how concepts relate within this domain of interest. So typically what we build in KR are things called knowledge bases. A knowledge base, formally speaking, is a pair that consists of two entities. The first entity is called a database or an A box, and the database or A box contains what's called assertional knowledge or factual knowledge. So if you've ever studied first-order logic before, essentially the A box contains atomic formulae. So this contains things that express that objects stand in relations to each other or satisfy certain properties. For instance, if we were creating a knowledge base for a university, the A box might contain information on the students. So it might say person X is a student, person X has student ID number N, person X is taking class C, and so forth. Right? So this is the kind of information that's in the A box. I'll be giving an example of a knowledge base on the next slide, by the way, to make this very precise. So that's what's in the A box, and the second component of the knowledge base is called the T box, and this is essentially a logical theory. The T box contains typically two kinds of formulae or expressions. It contains what are called definitions. So a definition just defines a concept or a term. Right? For example, a definition is, you could say something like, someone is a lecturer if and only if they are employed by a university and they teach at least one course. Right? This is an example of definition of lecturer. That could appear in the T box. And additionally, you could have in the T box if-then statements, which talk about how certain concepts or predicates relate to one another. For instance, if you are a professor, then you are an employee. Right? If you are a student, then you are taking at least one course, things of this nature. So the T box is really about relating concepts that are, or predicates that are used or applied to entities. Now, as stated above, we want to do automated reasoning with these knowledge bases when we encode information in a knowledge base, there's thousands or tens of thousands, even more, of formulae, so it's not feasible to carry out reasoning by hand. We need to have algorithms to do this for us. And the standard reasoning problem that we encounter in KR is how to query knowledge bases. So all a query is it's some expression represented in a logical language, and if it's a Boolean query, you will get a yes or no answer back. So if it's a logical consequence of your knowledge base, then the answer to the query is yes. And if it's not a logical consequence, then the answer to the query is no. And there are other kinds of queries as well. Okay, so that's just a little bit about knowledge representation. And let me talk about or give an example of a specific knowledge base to try to make these definitions that I've explained at a high level concrete. So the knowledge base is shown on the top of the slide. It consists of these two components, the A box and the T box, as I mentioned previously. And I'm using a description logic language here to encode information. I'll explain how to read each of these formulae so you can interpret them. Though in lectures 3 and 4, there will be some discussion of description logic, so you'll get an introduction to these languages later on. So in the A box, we have this assertional knowledge, as I mentioned, encoding facts about some domain of interest. And this knowledge base is very basic because it's serving as an example, but it's encoding information about notions concerning forests and land. So in the A box, we say that some object E is a forest ecosystem. That's what this first formula says. The second formula is expressing that E is associated with or has some land L. And the third formula is saying that L has some area that is greater than or equal to half a hectare. So you can see that the A box is just encoding properties of entities or relationships between entities, right? The T box, on the other hand, is encoding definitions and relationships between concepts. So the first definition defines what it means to be a forest in this setting. A forest is defined to be something which is both a forest ecosystem and, this stands for logical conjunction, it has some land that it's associated with, such that the area of that land is greater than or equal to half a hectare. Okay? The second definition is saying that something is a forest ecosystem if and only if, so that's what this tri-bar stands for, is if and only if, it is an ecosystem and it's the case that its tree canopy cover is greater than or equal to 20%. So these serve as definitions, and the last formula in the T box is serving as an if-then statement, relating concepts related to area. So for example, it says that this is can be thought of as logical implication, saying that if something has an area that's greater than or equal to half a hectare, then it's not the case that the area is less than half a hectare. Right? So this is the example knowledge base representing what I had described on the previous slide. And of course, as I mentioned, you can query it. You can ask this knowledge base questions. So we could, for example, ask if E is a forest according to this knowledge base. And it's not hard to see that that's true. So we have that E is a forest ecosystem, right? And there is some piece of land that it's associated with. So there exists something that it's associated with such that its area is greater than or equal to half a hectare. So that means that E satisfies the right-hand side, the definitions of this definition, and therefore it satisfies the left-hand side of the definition, the definiendum. So the answer to query 1 would be, yes, it is the case that E is a forest according to this knowledge base. Query 2 is obviously going to be false, and this has to deal with the last formula in the A box, which says that L has an area greater than or equal to half a hectare. And then by this if-then statement in the T box, we know that if something has greater than or equal to half a hectare, it's not the case that its area is less than half a hectare. So this is false. Yeah? Okay, so that's just a quick example of a knowledge base and querying that's done on it. Let's talk about an important problem that pops up in the context of knowledge representation called knowledge integration. So knowledge integration is a problem that pops up when we have multiple knowledge bases designed by different people or groups or institutions. When knowledge bases are designed, when you want to try to model a domain of interest and represent it in some logical language, you have to make decisions on how you're going to apply predicates or relationships to talk about entities within that domain of interest. Right? So when I make a knowledge base, I have certain criteria for when I apply predicates and when I do not apply predicates. This means that knowledge bases are always constructed from a certain point of view with a certain language use. And now the thing is that from your perspective, you can create a knowledge base which encodes some domain of interest or represents it, and your reasoning can be perfectly consistent, logically consistent. But someone else can come up with a different knowledge base, which also is consistent. However, when you put them together, you'll run into trouble, and there will be inconsistencies or contradictions that arise. Okay? That's essentially the knowledge integration problem. How do we take multiple sources of knowledge, multiple knowledge bases, which are potentially conflicting, and put them together in some way to be able to reason in a logically consistent manner and avoid contradictions? So to try to demonstrate this problem, I've given an example on this slide of technically 3 knowledge bases. So the first knowledge base, KB1, is what is called the land cover standpoint. So this knowledge base is just encoding, in this example, one perspective of what it means to be a forest. So in KB1, we say that some object E is a forest. Okay, so that would occur in the A box, right, since it represents assertional knowledge. We have that a forest is defined as it was in the previous example. Something's a forest if and only if it is a forest ecosystem. And it has some land that it's associated with, such that its area is greater than or equal to half a hectare. And last, we have that if something is a forest ecosystem, then it is an ecosystem. Okay, so this is called the land cover perspective of a forest, where a forest is really associated with some plot of land that's taking up some certain area. And the second knowledge base, we call this the land use perspective. This is a different way of, say, talking about forests that someone could construct. So we have that L is considered a forest in this perspective. And a forest is defined as follows. We have these 2 formulae in the definitions, the defining phrase of this definition. And the first says that so something is a forest if the land that it is associated with has been designated to be used as a forest. Okay, so that long phrase is encoded in this very simple formula. Essentially what that means is that, for example, this area of land has been deemed a natural reserve, or it's been deemed to be used for logging purposes, something like that. Okay? And we have that this area is maximally connected, so it doesn't consist of disjoint patches. So this is the land use perspective of what it means to be a forest. And if you have that some piece of land has been designated to be used for forestry purposes, then it's the case that it's a piece of land. All right? And we have an additional ontology or knowledge base, which is called the basic formal ontology, which I'm assuming exists in this example, that encodes relationships between certain natural language concepts. And I'm going to assume in this example that KB1 and KB2 inherit at least this formula from this basic formal ontology, which says that the concept of land and ecosystem are disjoint from one another. And it says that if something is both considered land and an ecosystem, then a contradiction arises. I mean, the way that we use the term land in natural language, it represents some sort of geographic area, right? Whereas ecosystem is a system of organisms that are sort of self-sustaining. So these are 2 distinct things. Now, I'm going to assume that KB1 has this implication associated with it and KB2 as well. And we can see that if we try to force a merge between these different knowledge bases, that a contradiction arises. And I can sketch up the proof of this on the board. So if we take this fact and apply this definition to it, starting with the fact that E is a forest, I can derive by means of the definition that if something's a forest, it's a forest ecosystem and satisfies some other property, that E is a forest ecosystem. And then by the last formula in KB1, I know that E is an ecosystem, right? So ecosystem. Okay. Now, since I'm assuming that I've merged these knowledge bases together, I also have access to the second definition. And since E is a forest, this means that E has been designated to be used, or its land has been designated to be used for a forest. So we have E, forest, land use, also as a consequence of that definition. And by the third formula, this means that E is considered a piece of land. Whoops. And now, with the fact that we have that E is an ecosystem and E is considered a piece of land, by this implication here, I have that E satisfies falsum, or bot as it's sometimes called. So falsum serves as in this example, as a unary predicate, and it typically represents logical contradiction, if you've ever taken a course in logic before, and nothing is allowed to satisfy falsum or bot. So this leads to an inconsistency when we merge these different knowledge bases together. So the problem arises, right? How do we avoid this logical contradiction in this particular example and also in general? And there are various ways that one can try to avoid inconsistencies. So one technique that people have applied is to try to find the source of the inconsistency. In this particular example, we saw that there are two definitions of forest, one in each knowledge base. And what one could do is remove one of those definitions in the merge to try to obtain a consistent knowledge base. But when you do that, you lose information. So this is not entirely satisfactory. You also have the practical problem that in real life, knowledge bases are incredibly large. And so trying to find the source of the inconsistency can be quite difficult. And this is not entirely a satisfactory solution. So what we're going to do instead of, for example, removing information or duplicating predicates is we're going to wrap each formula from each knowledge base in something called a standpoint modality, which is an additional kind of logical connective. Okay? So instead of forcing the merge of these knowledge bases, what we do is we take all of the perspectives as they are and reason with them simultaneously and wrap the reasoning in these modalities. So for instance, in the land cover perspective, I have this implication. I can wrap it in what's called a standpoint modality, which says that from standpoint LC, it's the case that if something's a forest, then it's an ecosystem. Right? If I were to reason with the second knowledge base, I would be able to derive that if something's a forest, it's a piece of land. So that's true from the land use standpoint. Okay? So by adding these modalities, we avoid the inconsistencies that might arise when we merge the knowledge bases. And as an added bonus, the computational complexity of adding these logical connectives, which is one has to be careful of when extending a logical language, when we add these new logical connectives to our knowledge representation languages, it turns out that the computational complexity doesn't rise very much. So if you're not familiar with computational complexity, it relates to how much time and how much space is used to run algorithms within that logical language. And so adding these logical connectives, these standpoint modalities, is not going to increase that by very much, as we will see. Okay? So standpoint logic is an answer to this knowledge integration problem. Let's now talk about standpoint logic, and we will start with the most basic version of it. Right? So propositional standpoint logic, which I'll also call SL throughout the course of this lecture and the next lecture. The language of standpoint logic is defined relative to what's called a vocabulary. So a vocabulary is a pair which consists of two sets, A and S. A consists of propositional atoms, or atoms as they're sometimes called. So P, Q, and R will be used, for instance, to represent propositional atoms. We assume that we have countably infinite number of them. And propositional atoms, just as in propositional logic, or Boolean logic as it's also called, just represent or just express a declarative statement. That's the way that we think of these, right? So they might say something like it's raining outside, or that object is blue, someone is a teacher, etc. So these are just used to express facts. They don't have any internal structure. The second component of a vocabulary is the set S of standpoints. We're going to assume that we have a finite number of them. And we use S and T sometimes with annotations like primes or subscripts to denote standpoints. And there's a special standpoint that exists in this set called the universal standpoint, indicated by this asterisk. The universal standpoint is essentially a standpoint that subsumes all others. And we'll go into more detail about the universal standpoint and its interpretation later. Okay, using this vocabulary, we can define a language L, as shown in the middle of the slide, by means of this BNF grammar. And our formulae are in what's called negation normal form, which means that negations are applied only to atoms. This will make our proof system later on a bit simpler. And we can define full negation, as I'll show on the next slide. So if you're not familiar with BNF grammars, I'll explain what this expression is encoding. BNF grammar is essentially a representation of a context-free grammar that defines a language in an inductive manner. And I'll talk about what formulae appear first and then explain how this BNF grammar defines inductively our language, which contains an infinite number of formulae. So we have, as a base case in this BNF grammar, statements called sharpening statements. This essentially expresses that S is sharper than T. Now, S and T are standpoints, and what this means is that the standpoint S inherits the information from standpoint T. That's the idea. So in the previous example, if we go back, we had that the land cover perspective inherited the perspective of the BFO, and same with KB2. Right? So it was sharper than that standpoint. I will be giving a formal semantics for this language as well that will make all these interpretations precise. We have propositional atoms in our language, which, as I said before, just represent some declarative statement. We have the negation of propositional atoms. So essentially they say that it's not the case that some proposition holds. We have conjunction in our language, which says that two pieces of information, phi and psi, hold jointly. We have disjunction, which says that phi or psi holds. And then we have our interesting standpoint modalities. So box S phi is interpreted as saying, from standpoint S, it is unequivocal that phi holds. So as I had alluded to earlier when talking about knowledge bases are constructed from a particular standpoint with language being used in a certain way. So there might be some variability from standpoint S in how language is used. What this modality is expressing is that regardless of how S is using language, phi is a true proposition. You can just think of it as essentially expressing that from standpoint S, phi is true no matter what. And then we have the diamond modality, which says that from standpoint S, it is conceivable that phi is true. So from standpoint S, based on the way that it is using language, it will potentially consider phi to be true. Okay? So as I said before, this BNF grammar encodes in inductive definition. And let me try to show you how it does that on the slide, in case you're not familiar. So essentially, in this definition, we have three base cases. And we have at the base of our language, which we can think of as some infinite union, we have these sharpening statements, right, which can be of various different forms using various different standpoints. We have propositional atoms, and we have their negations. Okay, so this serves as sort of the basis of the language. And there's an infinite number of these entities because we have an infinite number of propositional atoms in our language. Now, the next four clauses are the inductive clauses of this BNF grammar definition, which say that if I've already have at my disposal two formulae, phi and psi, for example, I can form a conjunction, a disjunction, or I can tag phi with boxes or diamonds. So this is going to build a hierarchy of formulae, these four clauses, and I can form conjunctions, for example. I can add boxes to the formulae that occur at this first level, and I can form disjunctions, for example, so maybe P or not Q, and this gives a second level in this hierarchy. And I can now apply these four clauses again with what's been constructed and make more complex formulae. So I can form conjunctions between formulae that appear at different levels, for instance. So S prime is T. And I can add a box operator, for example, to something that has occurred at a previous level, and so on and so forth. And so if you continue this process upwards, the union of all of these different levels gives you the language of propositional standpoint logic. So this formula shown in the middle of the slide, which is a context-free grammar represented in Bacchus-Nauer form, as it's called, is encoding or representing this inductive process and is defining this language for us. Okay, so It's enough on the language of standpoint logic. Let's talk a little bit about abbreviations and other logical connectives that will be used throughout this course. So as I mentioned on the previous slide, we have atomic negations in our language, which only apply to propositional atoms. Again, this is helpful for the way that we formulate our proof system for standpoint logic. And we can define a version of full negation, which will be used throughout the lectures. And full negation is defined as a recursive operation shown on the top of the slide. So full negation operation is defined as follows. If I apply full negation to an atom, I just get the negated version of that atom. If I apply full negation to a negated atom, I get the positive version. Applying the full negation function to a conjunction returns a disjunction, where I've applied full negation to phi and psi. Similarly, if I apply full negation to disjunction, it becomes a conjunction where I've applied negation to phi and psi. And applying full negation to a box operator pushes the negation inwards and flips the box into a diamond. And similarly, applying the full negation operator to a diamond flips it to a box and pushes the negation forward. So essentially what this function does is it takes a formula from our language and it outputs a formula in negation normal form, which serves as the negation of that formula. Okay? So here's an example of how that works. Here's a formula in our language. And if I apply this full negation function to it, I would apply this clause here first to switch the conjunction to a disjunction and apply the full negation operator to both disjuncts. I can then apply this clause here from the definition to switch the box into a diamond and put the negation on the propositional atom P. And applying full negation to a negated atom just returns the positive version of that atom. So this formula serves as, in our language, the negation of this formula. They express opposite states of affairs. And they're, in fact, contradictory with one another. If you take a conjunction of them, this implies falsum. Okay, there are other connectives that we're going to use throughout this course. For example, the top or verum connective, which just represents tautology, so something that's true. And we can fix a propositional atom P and disjoin it with its negated version to represent top or define it. We have falsum or bot, as it's also sometimes called, which represents logical contradiction. We can define this again by fixing a propositional atom P and conjoining it with its negated version. Implication can be defined relative to our language by taking the full negation of phi and disjoining it with psi. So this is, in classical logic, these two formulae are equivalent to each other, and we here are forcing their equivalence by means of a definition. And then in the standpoint setting, because we're talking about different standpoints and the ways in which they use language to reason about and talk about the world, we have these special modal operators that can be defined in terms of these standpoint modalities. The first operator is called the determinacy operator. And essentially what this says at a high level is that from standpoint S, the meaning of phi is determined. So you can define that, as shown here. This formula says that from standpoint S, it is completely the case that phi is true. It is unequivocal that phi is true. Or from standpoint S, it's the case that phi is false. Right? That's what it means for its meaning to be determined from a particular standpoint. You either always consider the formula true or always consider it false. And then we have the indeterminacy operator, which will be occasionally used. And the indeterminacy operator expresses that from some standpoint, the meaning of a formula is not necessarily determined. So from standpoint S, it's conceivable that phi is true. And it's the case that from standpoint S, it's conceivable that phi is false. And so this means that from standpoint S, they're not entirely sure whether to interpret phi as a true or false proposition. Okay? And again, this deals with how meaning is understood in standpoint logic. Okay, so let's try to represent an example by means of standpoint formulae to kind of demonstrate the modeling capacity of standpoint logic. So in this particular example, there are three different standpoints. There is the common sense standpoint, which I'm denoting by C. So this example has to deal with how color classes are considered and how the names of colors are actually applied from different standpoints. So from the common sense perspective, we say that blue and green are disjoint categories. So something is not both blue and green, it's either blue or green from this common sense perspective. And we can encode this fact, represented in natural language, by the following standpoint formula, which says that from standpoint C, it's not the case that anything is both blue and green simultaneously. We have also in this example what's called the house painting perspective, or the perspective of a house painter, if you will, which extends the common sense perspective, meaning it takes the common sense perspective of colors and extends it with some additional information. So that's represented by the sharpening statement that I brought up earlier. The statement says that standpoint H is sharper than standpoint C, so H is inheriting C's perspective. And we have that from the house painting perspective. If something is teal, then it's considered green in this example. And we can represent that fact by means of this standpoint expression or formula, which says that from standpoint H, it's unequivocal that if something is teal, then it's green. And the last standpoint, which I'm denoting by R, represents the standpoint from the RYB color model perspective. And there, teal sits between both blue and green. So from this standpoint, if something is teal, it's the case that it's both blue and green simultaneously. So we're going to use this color example as a fairly simple example throughout this lecture to talk about propositional standpoint logic. Okay, so that shows how some natural language sentences or a scenario can be modeled in propositional standpoint logic. What can we infer from these statements? Well, it's not hard to see, given that the house painting perspective inherits the common sense perspective. And from the common sense perspective, nothing is both blue and green simultaneously. One can infer, using just their natural reasoning, that from H's perspective, or standpoint, it's not the case that anything is both blue and green. And then using this fact in conjunction with F3, which says that from standpoint H, if something's teal, then it's green, you can infer that from standpoint H, if something is teal, then it's not blue. Okay? And we can see that this contradicts or is inconsistent with standpoint R, where if something is teal, then it's blue and green, or a fortiori, therefore it's blue. Because if the house painting perspective, from that perspective, one were to witness a teal object, they would call it not blue, based on the way they're using language and applying predicates. Whereas from standpoint R, if they were to encounter a teal object, they would call it blue. So what happens here is that we have some inconsistency between different perspectives or standpoints, but because we're wrapping our formulae in these standpoint modalities, we are avoiding this inconsistency. Okay? All right, so that was material on the language of propositional standpoint logic. What I'm going to talk next about is the semantics. So the model theory for standpoint logic and how we interpret these formulae over specific kinds of models or structures. Now, standpoint logic grew out of a particular philosophical theory called supervaluationism. And you don't need to have an incredibly in-depth understanding of this, but a superficial one to understand the mathematical models. But this serves as the basis or justification for the models that are used in standpoint logic. And supervaluationism is an idea that tries to explain vagueness or semantic variability in language. And the idea goes back to Kit Fine. And the idea is that the semantic variability of natural language can be explained by the fact that language can be interpreted in many different yet equally acceptable ways, which we call precisifications. So inside of our models that we're going to use to interpret these standpoint formulae in the propositional standpoint language, we're going to have specific points which are called precisifications. And philosophically speaking, a precisification is taken to be a complete and consistent way of making a vocabulary precise. Again, this relates to what I said earlier, where when we design, for example, a knowledge base, we have to come up with certain criteria for how we apply terms or predicates. And a precisification is essentially thought of as a way of doing that in a complete and consistent manner. Now, from the perspective of supervaluationism, there is no actual precisification, right, because The semantic variability of natural language, from this perspective, is explained by the fact that you can have multiple ways of interpreting language and have complete logical consistency of reasoning within those interpretations in the way that you're using terms, but there is no actual one which is correct. Right? Now, for us, a standpoint is going to be viewed as a set of precisifications, which represents essentially a partial semantic commitment. So from a particular standpoint, one might have multiple ways in which they use language, and this is encoding this fact. So let's make these models precise that are based on this philosophical idea. Standpoint models, also called standpoint structures, are mathematical objects represented by M, which are encoded as triples, consisting of 3 different parts. The first part, big pi, is a set which has to be non-empty of precisifications. So mathematically speaking, these are just points in your model, but they're representing, as explained on the previous slide, some way in which you can make language, you can precisify your language and make it completely consistent. And we have a function sigma, which interprets standpoints as collections of precisifications. So this will represent this will map each standpoint, right, to a non-empty set of precisifications. This 2 to the pi, by the way, means the power set of pi, if you're not familiar with this notation. And because we exclude the empty set, this means that from every standpoint, it has to be the case that there's at least one precisification, at least one way in which they can make their vocabulary precise in order to carry out reasoning. Delta is called a valuation function. It maps each atom to a set of precisifications, and the idea is that those atoms, which represent declarative sentences or express a proposition, are true in those precisifications. Okay? So if you've ever studied modal logic before, these models are very similar to Kripke models, and you can actually transform these into Kripke models and vice versa. But they have a fairly basic structure. They're essentially a set together with some function that determines specialized subsets, and then a valuation function which interprets atoms as being true or false at particular precisifications. Note there is a restriction on sigma, which is that the universal standpoint ranges over all precisifications. So the universal standpoint is essentially taking into account all standpoints and all admissible precisifications. Okay, so here's an example of a standpoint model. I'll go through it and explain it. So if S is our set of standpoints, we have S and T, and we have the universal standpoint. We have in this model that pi, the set of precisifications, consists of 3 points, pi 1, pi 2, and pi 3. The interpretation of S is considered to be this blue oval shown here that contains pi 1 and pi 2. And the interpretation of T is just the singleton shown here that contains pi 3. And then, of course, the universal standpoint has to range over all precisifications, so it's just equal to pi. And then, of course, atoms would be mapped to these precisifications as well. I just haven't represented them here. Okay, we're going to use these standpoint models to interpret our formulae. So that is explained on this slide. On the top of the slide are the semantic clauses or truth conditions for interpreting propositional standpoint formulae over these standpoint models or standpoint structures, as they're equivalently called. And I've also given an example to demonstrate how to judge the truth of propositions relative to a given model. Okay, so let's go through it. The way that you determine, so in standpoint logic, you determine satisfaction of a formula or truth of a formula relative to a given model and relative to a precisification in that model. So this is very similar to how things are done in Kripke semantics, right? So the way that we determine that P is satisfied or true at a model M in precisification pi is by checking the delta function. Right? So we have inside of our model essentially the base case of this recursive definition. And if pi is in delta of P, in other words, delta deems that P is true at pi, then we say that P is satisfied on M at pi. Okay, so for example, P is mapped to pi 1 and pi 2. It's taken to be true at those precisifications in this model, right? Or in particular at pi 1. We have that the negation of a propositional atom is true at a precisification pi in a model M if and only if it's not an element of delta of p. So for instance, right, q is not mapped to pi 2, therefore not q is true there. Right? So this enforces a type of classical reasoning at precisifications. Either a formula is true or its negation is true. We have that phi and psi, a conjunction is true in a model M and a precisification pi, if and only if phi is true there and psi is true there. Right? So for instance, we have in our model that p and q were mapped to pi 1. Therefore, p and q is true at pi 1. We have that phi or psi is true in a model M and a precisification pi, if and only if either phi holds there or psi holds there. So for instance, we have p holding at pi 2, therefore p or q holds at pi 2. And now we have the interesting clauses, which deal with the standpoint stuff, going beyond just regular Boolean logic. The first clause tells us how to interpret standpoint boxes. So we have that S box phi holds at pi in M, if and only if it's the case that phi holds in every precisification pi prime in sigma of S. So essentially what this means is that from standpoint S, phi holds in all of its precisifications. Regardless of how it's precisifying its language, it will consider this a true proposition. That's the idea. And inside of this example model, right, we have p holding at pi 1 and pi 2. So we have box S p holding at pi 1, for instance. We interpret the diamond as follows. Diamond S phi holds at pi in M, if and only if there exists a precisification pi prime where phi holds, and that precisification is in the interpretation of S. So for instance, Q holds at pi 1, therefore we can say diamond SQ holds at pi 1. And last we have the sharpening statements, which are encoding the intuition that I mentioned earlier, that standpoint S inherits the information from standpoint T. So S is sharper than T in M at pi, if and only if it's the case that the interpretation of S is in fact a subset of the interpretation of T. Now in this example model, we have that the interpretation of T is this green oval, which serves as a subset of the purple one, which is the interpretation of S. So we can say that T is sharper than S. All right? Now one thing to point out, which actually relates to why propositional standpoint logic and other standpoint logics have a low complexity, is that these three standpoint expressions, the boxes, the diamonds, and also the sharpening statements, have a particular property, which is that they are precisification independent. If it's the case that they hold at some precisification, then these formulae also hold at every precisification. They hold globally as well. So what this means is that to check if one of these formulae is true, it's typically enough to just look at some world or the current world or precisification that you're at inside of this model. So satisfaction and global satisfaction coincide for these standpoint expressions. Okay, so those are the truth conditions that we use to interpret standpoint formulae. And next, what I'm going to talk about are different classifications of formulae in standpoint logic. And these are helpful, in particular with respect to our proof theory, because checking if formulae satisfy some of these conditions or definitions is tantamount to determining if formulae are logically consistent or for determining if a logical consequence holds between formulae. So if you've taken a course in logic, you're probably familiar with these, but I'll go through them anyways, just so we're all on the same page. We define a formula to be satisfiable if and only if you can find a model and a precisification which makes that formula true. Right? So satisfiability is the ability to be made true, and the opposite of this is unsatisfiability. So phi is unsatisfiable if and only if for any model and precisification you look at inside of that model, phi is false. So unsatisfiable formulae are what some people call contradictions. They're formulae which can never be made true. We have that a formula is valid if and only if for any model and any precisification in that model, phi is true. So essentially a valid formula is a tautology. It's something which is true no matter what. So if you want to check, for instance, if a query follows from a knowledge base, right, you can represent the knowledge base as a formula, since it's a finite object, and you can check if the knowledge base implies the query. If that's a validity, then it's the case that the query is true according to that knowledge base. So validity can be used for query checking. And invalidity is the opposite of validity. We have that a formula is invalid if and only if you can find a model and a precisification, which makes that formula false. So invalidity is the ability to be false. And there are certain relationships between these different categories of formulae. And so if something's valid, then its negation must be a contradiction. It must be unsatisfiable. Right? If something's satisfiable, then its negation is invalid. And as I mentioned before, right, satisfiability and unsatisfiability are contradictory with one another and similar for valid and invalid. The proof system that I'm going to define a little bit later is going to axiomatize the validities of standpoint logic. So validity will play a notion in understanding why that proof system works. Okay, let's return back to our color example from earlier. And I'm going to show why the different standpoint formulae from that example are consistent. And one way of demonstrating consistency in logic is providing a model for the formulae. So if you can provide a model, it means that the formulae are jointly consistent with one another. So in the earlier example that we looked at, C was the common sense standpoint, H was a house painting standpoint, and R was the RYB color model. And we had that from standpoint C, it was unequivocal that nothing is both blue and green. We had that the house painting standpoint inherited the common sense standpoint. And we had that from standpoint H, if something was teal, it was considered green. And from standpoint R, if something is teal, it's considered both blue and green. Okay? So we can provide a model for this example, as shown here in the middle right of the slide. Right? We have two precisifications, pi1 and pi2. And at pi1, we make teal true, green true, and blue false. So essentially, from this standpoint, some object is teal, green, and not blue. And from pi2, in this precisification, we have that teal is true, green is true, and blue is true. We interpret the standpoint R as just the set containing pi2, and we interpret the common sense and the house painting standpoints to just be the set containing pi1. Okay? And then, of course, as is always the case, the universal standpoint includes all precisifications in the model. Now, it's not hard to see that all these formulae are jointly satisfied. Right? So we know, for instance, that at every precisification, according to standpoint C, which is just pi1, we have that blue is false. So from standpoint C, it's not the case, right, that some object is both blue and green, because according from this precisification, some object is green but not blue. We have that H is sharper than C in this model, because I've made their interpretations equal. So therefore, by the semantics, the interpretation of H is a subset of the interpretation of C. We have that from standpoint H, teal implies green, because in pi1, so every precisification in the interpretation of H, we have that teal implies green, because teal and green are both true there, so this implication is true. And last, right, we have that at precisification pi2, that teal, green, and blue hold, therefore this implication holds. And this is every precisification that occurs in the interpretation of standpoint R, so we have box R, that implication holding. So this model is witnessing that these are jointly satisfiable, even though it was the case, as we saw earlier, that these standpoints are inconsistent in a certain sense, right? So which can be expressed as shown on the bottom of the slide by using the indeterminacy operator. So in this example, right, at pi2, we have blue being true. So from the universal standpoint, it is conceivable that some object is blue, because that's true in pi2. And we also have that from the universal standpoint, it's conceivable that some object is not blue. So what this means essentially, right, is that blue is an indeterminate predicate. The way that language is being used, or terms are being applied from standpoint C and H, in contrast to standpoint R, are different from one another. Right? Presented with a teal object, right, the house painting perspective would say that it's teal, but it's not blue, while from the RYB color model perspective, they would say that object is in fact blue. Right? So this indeterminacy operator is encoding or explaining this discrepancy between these different standpoints. And this is one way in which standpoint logic is quite nice. Not only can you reason jointly with knowledge bases that might be inconsistent with one another, but you can also identify where these inconsistencies arise. So what formulae are considered different from different standpoints. Okay, so that covers the material on propositional standpoint logic. I'll say let's take a 5-minute break, and then afterwards we will start discussing the proof system for standpoint logic. So let's reconvene at, say, 9:56. Yeah? Okay, let's reconvene and start the second part of this first lecture. So we went over the language of propositional standpoint logic and motivated it by means of the knowledge integration problem. And we also talked about the semantics of standpoint logic, right? These standpoint models or structures, as they're called, and how to interpret formulae over them. What we're going to now talk about is the proof theory of standpoint logic. So we're going to talk about the construction of a proof system which allows for us to do automated reasoning with standpoint formulae and to automatically check validity and invalidity of formulae. So before we talk about this proof system, we'll talk a little bit about proof theory and what it is. Proof theory is one of the 4 primary branches of mathematical logic, along with recursion theory, set theory, and model theory. And in proof theory, what we do is we study the notion of proof, and also proof system, which are used to construct proofs, as mathematical objects in their own right. So since arguments within a logical or mathematical theory can be represented as a mathematical structure, we can use formal techniques to manipulate them, to prove facts about logics, and to even extract information about logics from these types of structures. Now, these things which are called proofs, or also called derivations, are constructed within something called a proof system. And proof systems come in many different forms and varieties, but they typically all share one thing in common, which is that they are collections of 2 kinds of entities. First, they consist of objects which are called axioms. So these are essentially formulae that are assumed to be true from the standpoint of your logical or mathematical theory. So for instance, in number theory, there are various axioms that are used, like for instance that no number is smaller than 0. I'll just write these on the board so you have access to them. So in number theory, right, an example of an axiom is it's not the case there exists some x such that x is less than 0. Another axiom of number theory is that if I add 1 to x and add 1 to y, and the result is equal, then it's the case that x is equal to y. Right? And in logic, we have various axioms that we use. So sometimes P implying P is an axiom in logic. This is a very basic one that we should all agree with. Right? If P is true, then it is considered true. In propositional logic, for instance, you also have what's called the weakening axiom, which says that if P is true, then it's a consequence of anything. And so depending on what mathematical or logical theory we are dealing with, we can have different axioms which represent fundamental truths about that logical or mathematical theory. So axioms are essentially the starting point of proofs. And we can manipulate axioms by means of inference rules. So inference rules can be thought of as types of functions. They have some number of premises, and they take these premises and they let you derive a conclusion, a new piece of information on the basis of what has been given. So a famous inference rule in logic, which I assume most people have encountered, is the rule of modus ponens. There's not much room on this board, so let me erase. So modus ponens says that if some piece of information phi is true and phi implies psi, then I can conclude that psi is true on the basis of these 2 pieces of information. So inference rules consist of axioms, proof systems consist of axioms and inference rules, and you can construct proofs by starting with axioms and chaining inference rules together to derive new formulae or information, which we call a theorem. Okay? So a theorem is a conclusion of a proof. And as I said before, there are a lot of different kinds of proof systems that exist in the literature. There are Hilbert systems, which if you've taken a first course in logic, you've probably encountered. So these are basic axiom systems. You just have some set of axioms, usually with modus ponens and perhaps one or two other rules. There are natural deduction systems, sequence systems, tableau, resolution. I'm not going to go into detail about all of these. What is important for us and for standpoint logic is the kind of proof system that we are going to use, which has been around for maybe about 30 or 40 years now, and these are called nested sequence systems. So the proof system that we are going to design and provide for standpoint logic is going to use what are called nested sequence. Nested sequence are essentially trees, certain kinds of labeled trees, where the nodes of those trees are multi-sets of standpoint formulae. And this will be the basic building block of our proof system, and we will construct proofs using these nested sequence. Okay? Now, one of the reasons why we want to provide proof systems for logics is because they not only allow us to carry out reasoning in a formal manner by means of these proofs that are constructed, but also because we can use proof systems to write decision algorithms. There's a lot of different kinds of decision algorithms, which, if you're not familiar with what a decision algorithm is, it's a way of determining if a formula is valid or invalid for a particular logic. And one way of doing that is to write what's called a proof search algorithm. What a proof search algorithm does is it takes a formula and it tries to find a proof of it. And if it finds a proof, you know the formula is valid. And if it's unable to find a proof, then the formula is deemed invalid by the algorithm. So this is a helpful way of being able to decide the validity of formulae, which is tantamount to deciding logical consequence or querying relative to knowledge bases. And one thing which is nice from the proof theoretic perspective is that since the algorithm constructs a proof when something is valid, it gives you a witness or a certificate which tells you why that particular formula is valid, why that logical consequence holds. And when it's the case that proof search fails, usually you can construct a counter model which tells you why some logical consequence does not hold. So it gives you additional information about why something is valid or invalid. And the proof system that we're going to introduce can be used to define one of these algorithms. But more on that later. First, we're going to talk about nested sequence. So as I said before, these are the basic building block of our proof system. And the definition is a little bit cumbersome, so let's go through it bit by bit. A nested sequent is a type of expression of the form gamma turnstile delta, or also called the sequent arrow. And I have BNF grammars shown here which define the gamma and the delta that appear in this nested sequent. So the left-hand side of the nested sequent is called the antecedent, and it will consist of just a set of sharpening statements, okay, which we saw previously. So it consists of a set of these statements which tell us how standpoints relate to one another. And you can define gamma by means of this BNF grammar, and it says that a single sharpening statement counts as an antecedent. The empty set counts as an antecedent, and given two sets of sharpening statements, I can union them together by means of this comma to obtain a new antecedent. So this BNF grammar is essentially defining that the antecedent is a set of sharpening statements. Delta has a much more complex structure than gamma. Delta essentially is a tree of depth 1, at most depth 1, that has as its nodes multi-sets of standpoint formulae. So before I explain delta, let me explain sigma, since the definition of delta relies on sigma. So sigma here, this BNF grammar, is defining a multi-set of standpoint formulae. So a single standpoint formula counts as an object of type sigma. The empty set counts as object of type sigma. And given two multi-sets, I can union them together to obtain a new multi-set. Right? So the comma here is thought of in a multi-set fashion, while over here it's thought of it as in a set fashion. Okay? And delta is defined to either be a multi-set of standpoint formulae Or, given an object of type delta, we can add as a suffix to it a nesting, it's called, which is tagged with or labeled with a particular standpoint symbol and has inside of it a multi-set of standpoint formulae. Okay, so this expression is a little bit complicated, but really what it's encoding, as shown in the middle of the slide, is a tree of at most depth 1. So just a little bit of terminology before I talk about this. We call gamma, as I said before, the antecedent, delta the consequent, and each of these multi-sets that appears inside of the consequent, delta, is called a component. Okay? So the left-hand side is a fairly simple structure. Let's look at the right-hand side, the consequent. We can represent this, as I said, as a tree of depth 1. We have sigma naught, which could contain any number, even 0, of standpoint formulae. This serves as the so-called root component of this tree. And then each nesting can be thought of as representing an edge that is tagged with a standpoint symbol to this particular child's multi-set, okay, all the way up until n. So this is the structure of a nested sequent. Right? It's called the nested sequent because we have these nestings that have these multi-sets occurring inside of them. All right, let's look at some examples of nested sequence just to try to make this as concrete as possible. In the first example, the left-hand side of the nested sequent is empty and contains 0 sharpening statements, and the right-hand side is encoding a tree of depth 1 that has 2 nodes in it. So the root node contains this disjunction formula. Then we have an S prime nesting, which gives rise to this edge, which has stored at the child node this multi-set of 2 formulae. In the second example, we have a single sharpening statement in the antecedent, and we have the following consequent. By the way, there are these, which I didn't mention earlier, there are these little pies that tag these nestings. You can ignore these for now. Okay, these are going to be used a little bit later to define inference rules that operate over these nested sequence, but they don't really have any semantic meaning. They just have they're just useful in formulating inference rules. So anyways, to continue this example, right, the root of the tree of depth 1 is this multi-set. Right? We have an S prime child that ends at P, and an S child that ends at not P. Okay? So these are our nested sequence. And the question that comes next is, how do we interpret these nested sequence? And this slide shows how to interpret these by means of a standpoint formula. Now, this is typically the case for sequent calculi. If you've ever studied sequence systems before, you can typically interpret sequence, which are, in a certain sense, meta-expressions that are used to manipulate the formulae in some logical language. You can interpret them directly in that logical language itself. And this slide shows you how to do that. So given a nested sequent of the form gamma turnstile delta, where delta has this particular shape, which is the general shape of a consequent, we're encoding a tree of at most depth 1, the formula interpretation, which is denoted by iota, takes that nested sequent and maps it to the following formula. And we really view a nested sequent as being logically equivalent to its formula interpretation. So how is a formula formed by means of a nested sequent? What we do is we take a conjunction of everything in gamma of the antecedent. We think of the turnstile as expressing an implication. And we think of delta as representing a very complicated type of disjunction. We take a disjunction of everything in sigma naught, the root component, and then we take a disjunction over the following expression. So each of these nestings gets represented as a standpoint box modality, and we take a disjunction of each of the multisets that occur inside of the context of that standpoint box. Right? So essentially, if a nested sequent is valid, then that means that all of the sharpening statements in gamma taken together, if they're true, imply that some formula in sigma naught is true, or that from some standpoint, it is unequivocal that one of these disjunctions is true. So some formula within one of the child components is true. So this is the way in which nested sequents are interpreted, and as I said before, we really think of them as being logically equivalent. So a nested sequent is valid or invalid, or satisfiable or unsatisfiable, if and only if its formula interpretation is. And using this formula interpretation will be helpful for understanding why the rules that appear in our nested sequence system are sound, why they derive valid formulae. So here's an example of the formula interpretation shown on the bottom of the slide. We have a single sharpening statement, which occurs as the antecedent. Note that, by the way, this little ellipsis that appears here is representing this nested sequent. It's just that if I put it on the bottom of the slide, it makes the formula too wide. So imagine that the nested sequent is the input of iota. And we take a conjunction of everything in gamma to obtain the antecedent. The sequent arrow is represented by the implication. And then we form a complicated disjunction using the consequent. So we take a disjunction of everything in the root component. It's represented here. Then we transform each nesting into a standpoint box, where we've taken a disjunction of everything inside of that nesting. Since it's just a single formula, it's just a P in this case. And likewise, we can transform this nesting into this standpoint box here. Okay. So that is the way in which nested sequents are interpreted. And if you'd like to read up a little bit more on this before the next lecture, which will continue talking about the proof theory of standpoint logic, there is a paper on the course webpage that explains all of this stuff. Okay. So let's talk about the semantic reading now. What I've explained on the last slide is how to interpret a nested sequent as, yes? Sure. You can ignore the parentheses if you'd like. You could or not. You could include them or not include them. It doesn't matter. Yeah. Oh, yeah. The question was, why are there parentheses inside of the context of the standpoint boxes, the last two, but not the first one? And the answer is that I wrote it that way, and they aren't absolutely necessary. Okay, so on the last slide, we talked about the formula interpretation of a nested sequent. We know how to interpret a nested sequent as a formula. We also know by what was said earlier how to interpret a formula semantically over a standpoint model. So we can bridge these two things together, obviously, to interpret a nested sequent directly over models. And that's what this lemma does, which I call the invalidity characterization. When we talk about the soundness of the inference rules that appear in our nested sequence system, we will typically phrase soundness in terms of invalidity. So there are two equivalent ways of talking about the soundness of inference rules in a proof system. First is that you can define a rule to be sound if and only if the validity of the premises secures the validity of the conclusion, or equivalently, you can say that if the conclusion of the rule is invalid, then some premise is invalid. So when we go about looking at the proof system, which we will do next time, we will prove soundness in this way using the invalidity characterization. And that's why it's important to understand that. Yes? Yep.
Why then do we write this specification pi I after every segment we don't use it? Because we use this square box, which we earlier discussed, independent of the.
So the question is, why do we have these tags on these nestings if we're not using them in the interpretation? Yes? Okay. What will happen is when we define inference rules that operate over nested sequence, we will have to apply those inference rules inside of specific nestings, and these labels will be important for identifying which nestings we can apply rules within and which ones we should not apply a rule within. So it's these tags, these pi i's, can be ignored for now, and when we look at these inference rules later in the next lecture, it will become apparent why they are useful. But from a semantic perspective, they do not have any meaning whatsoever. So this is just a piece of the syntax that's helpful for formulation, but it does not have a semantic reading. Yeah. Any other questions on this slide? If not, let's now talk about this lemma, which is going to characterize semantically what it means for a nested sequent to be invalid. So let this be a nested sequent. We say that it is invalid if and only if the following holds. There exists a model, M, and a precisification in that model, such that everything in gamma holds at pi naught, and everything at the root component, sigma naught, is false. And also, for each I, we can find a precisification in the interpretation of SI, such that everything inside of sigma I is made false. Okay? So essentially, you can think of a nested sequent as being invalid if and only if you can find a model which makes everything in the antecedent true and everything in the consequent false. Right? So let's go ahead and prove this to make this argument clear. So in this proof, we'll have a chain of if and only if statements which will express this equivalence. Let's first of all assume that gamma turnstile delta is invalid. So suppose we have some invalid nested sequent. Then by definition, by the previous slide, the formula interpretation of the nested sequent is invalid. And so that's just applying the definition. Now, we have that some standpoint formula, which iota of gamma turnstile delta is a standpoint formula, right? We have that some formula is invalid if and only if you can find a model and a precisification which makes that formula false. Right? That's just the definition of invalidity. Now, by the definition of iota, that means that on M, in this particular model that exists, at pi naught, we have this implication not holding. Right? So we're still just unfolding definitions. And now by the semantic reading of implication, which is a defined connective in our setting, but nevertheless, we can conclude that it must be the case that everything in gamma is true and everything in the consequent is false. So that's just the semantics of implication. And now continuing from that, if we have that this entire disjunction is false, then this means the first disjunction and the n-ary second disjunction are both false. Right? When a disjunction is false, all its elements are false. And now, if it's the case that this disjunction is not satisfied on the model, then its negation must be true. Likewise, for this big disjunction shown here, its negation must be true. And we defined full negation earlier. Right? We're taking this as a defined connective. And as we saw there, full negation is essentially a type of recursive function where the negation gets pushed inwards and it flips every operator to its dual, boxes to diamonds and vice versa, and conjunctions to disjunctions and vice versa. So what happens is that this negation operator applied to a disjunction will become a conjunction of negated formulae in sigma naught. And by the way, since I'm applying this negation operator to a multiset, I'll just show you what the definition of that is really quickly. So if I have a multiset of standpoint formulae, then when I apply the full negation to it, this is the same thing as just applying it component-wise to every member of the multiset. Okay? This notation will be used occasionally. And what happens here as well is that the negation gets pushed inwards, flipping every operator to its dual, and then the negation gets applied to each of the standpoint formulae in sigma I. Now, if we read what this last clause is saying, it's essentially saying the right-hand side of this if and only if statement. We know that there exists a model M and a precisification in that model, which makes everything in gamma true, which makes everything at the root component false, and where for each I, inside of the interpretation of standpoint SI, I can find a precisification that makes everything inside of sigma I false. Okay? So this lemma is telling you how to read nested sequence directly by means of models in the semantics. Are there any questions on that? Okay. So let's talk a little bit about notation that's used. This notation will be used to define or formalize the inference rules that will appear in our nested sequent calculus. And this is where the labels on nestings are going to come into play. So given a nested sequent, which generically has this form, we use this bracket notation to essentially talk about where specific instances of formulae occur inside of the nested sequent, which will be helpful for us to formulate our inference rules. This is in what is called the deep inference paradigm of proof theory. So we use this notation as shown here on the slide. If I have a nested sequent, and I have delta being the consequent, and I write in brackets a formula phi, and next to this set bracket I have a sigma I occurring, then what that is meaning, or what that is telling me, is that the formula phi is occurring in the child component sigma I. Okay? So this is how this notation is used. And if I have a nested sequent where I have delta on the right-hand side, and I have this set notation with a phi occurring inside, and a pi naught tagging it, this means that the formula phi occurs at the root component. Okay? So we specifically reserve this label pi naught to denote the root component, and then we use pi i's to reference child components inside of the nested sequent, which is encoding this tree of at most depth 1. Right? This will allow for us to represent our rules in our proof system in a very uniform and succinct manner. Okay, to make this notation concrete, let's look at a little example. So here is a nested sequence, and we represent the consequent by means of delta as usual. And there are multiple ways that we can represent this nested sequent in this notation that I've just described. So first, for example, I can have inside of the brackets diamond S naught P, and since that's tagged with a pi naught, that is telling me that this diamond formula is occurring at the root component of my nested sequence. Right? I have, for instance, P occurring inside of the pi 1 nesting. So this is a valid representation of this nested sequent in this uniform notation. Similarly, I have not P occurring in a pi 2 nesting, and so I can accurately write the nested sequent in this way as well. And there are other ways I could write it too. I could have, for example, box S prime P occurring inside of here instead. Right? So again, this is going to be helpful for formulating our inference rules. So we don't have time to go over the sequent calculus today. This is a quick snapshot of it. So let's save this for lecture 2. And next time what we'll do is we will talk about this nested sequent calculus. We'll talk about why these rules are sound, how they work, how proofs are built, and then we'll talk a bit about proof search, so how we can define an algorithm that automatically constructs proofs and checks the validity of formulae within co-NP complexity, or with co-NP complexity. So that is all for today.